Again, everybody. So this is a second example for chapter 22, dealing with a test charge in basically a uniform electric field. In this case, it's going to deal with two dimensions or a two-dimensional problem, because what the situation we have here is that let's imagine we have a charge, a test charge, in a uniform field that's pointing to the right. We're going to say this electric field has a strength of 1,000 newtons per coulomb. But it's a uniform field, right? So it's pointing, it's everywhere the same and pointing to the right. So for a positive charge, if I place it in this field, there will be a force of QE, F equals QE, pushing to the right along the field. Now the situation I have here is I'm assuming I have a charge tied to a light string that's attached to a support or the ceiling up here. So there's a tension in the string, right, that it's going to hold back the charge, hold the charge back from actually flying off to the right. Now we're going to assume that this charge is big enough, maybe it's a piece of paper or something that I put charge on, so it's got a mass, and so there's gravity, the weight actually pulling down as well. So I've got two forces, actually three forces now, mg going down, QE going to the right, and the tension at an angle here. Now the angle, maybe not totally clear in the picture, I should have drawn it bigger, but this is the angle theta I'm defining from the vertical to the tension or the strain in the picture. So typically, like what I do with forces in two-dimensional problems, I break everything into their x and y components. The electric field, force QE only has an x component, mg only has a y, so it's only the tension I have to deal with, right? So if this angle's theta, this is the opposite side of the triangle, and the x component is actually t sine theta. Whereas the y component going upward here is t cosine theta. It's the adjacent side to my angle theta. So once I've drawn that free body diagram, gotten all the components of the vectors, I can add up the x and y components of the force. To compute a number, we're going to say our charge Q is positive 2 microcoulombs, or 2 times 10 to the negative 6 coulombs. And the mass of the charge, or the little piece of paper that's on is 1 gram, 0.001 kilograms. But if I add up my x components, right, along this way, I've got QE minus t sine of theta. Now this is a static problem. The acceleration has to equal 0, right? So ma is 0, Newton's second law. So QE, the sum of the forces in the x direction, QE minus t sine theta has to equal 0. I can do the same thing also for the y components. I have t cosine theta minus mg, those are the two vertical or y components. They have to add up to 0 too, because there's no acceleration vertically. So I've got two equations, and the question that I want to answer is, what is the angle, right? What angle does it actually end up at here? So I've basically got two equations and two unknowns. I don't know the tension either, but I'm interested in the angle. So I'd like to get rid of the tension. One way to do that is to solve for t from the first equation or the second, right? In fact, what I did was solve from the y here. So I solve for t from the y component equation, and I get t equals mg over cosine theta. And I plug that into the tension in the x component equation. So I end up getting QE minus mg over cosine theta times the sine of theta equals 0. Sine of theta over cosine is tangent, so this is the same as QE equals mg tangent of theta. Again, just solving for the angle, theta is inverse tangent of QE over mg, right? And then I just plug in the numbers. So theta is the inverse tangent of QE over mg. Q was 2 times 10 to the negative 6. E was 1,000 newtons per coulomb. Mass 1 gram or 0.001 kilograms in g. Right, we're near the Earth, so it's 9.8 meters per second squared. Do that calculation, you'll get 11.5 degrees. Right, so the cable or the light string ends up 11.5 degrees from the vertical. Now I could, if I wanted, calculate the tension too, right? I could plug this theta back into either one of the two X or Y component equations and solve for T. But the main point again here though is that anytime I'm dealing with the electric field force, it's just another force. It gets added in as components, right? In our Newton's second law, some of the forces in the X equals MAX, some of the forces in the Y equals MAY. So those are my two examples for, or the previous lecture and this one are my two examples for force on a test charge. We also have talked about the source charges which create the field. Now we've talked about the test charge with it, which experiences the force due to the field. Okay, so I will stop there and see you soon.